welcome to the course on noise control in mechanical systems, and I am Professor Sneha Singh from the Department of Mechanical and Industrial Engineering at IIT Roorkee. So far we have been doing the module on noise measurement and instrumentation, and we have covered various aspects related to that, such as the typical acoustical devices that are used, what are the characteristics of these devices, the sampling rate, dynamic range, as well as the frequency range and various other characteristics of these acoustical devices. And at the same time we have also seen what are the measurement standards and the guidelines for a typical acoustical measurements in the field of noise control engineering. So, in this lecture, based on the understanding of the previous 3 lectures in this particular module, we will see some numerical problems on noise measurement and instrumentation. So, let us see the first problem. So, here it is given a 0.5 Pascal amplitude pure tone sound wave is measured using a microphone A with sensitivity of 20 microvolts per Pascal. What is the RMS voltage that would be produced by this microphone? So, let us first solve the first part of this problem. So, over here it is given that the microphone here 0.5 Pascals amplitude is being passed to it and the sensitivity is 20 microvolts per Pascal. So, for the mic A, what it essentially means is that all these sensitivities I would like to say is measured for microvolts per RMS pressure that is passed to it. Okay. So, here let us see. Okay. So, it has a sensitivity of 20 microvolt per Pascal. So, which means that if 1 Pascal of sound pressure is passed, be it an RMS pressure and amplitude, just the value of 1 Pascal of acoustic pressure, it will create a 20 millivolt of voltage when it is passed through this mic A. Okay. So, 1 Pascal input, 20 microvolts is the output. So, in that case if you think about is 0.5 Pascals amplitude should give a 20 microvolt multiplied by 0.5 as the voltage amplitude. So, this should be the amplitude to amplitude conversion. Okay. So, let us say for example, here we had some kind of acoustic pressure which had 1 Pascals, 0.5 Pascals is the amplitude of this acoustic pressure, and once it passes through the mic, you are getting the voltage. Okay. And here each of these 0.5 Pascal values, when they are converted into 20 into 0.5 microvolts, which is 10 microvolts. Okay. This is the sound signal, and this is the corresponding voltage signal generated by this microphone, and here the 0.5 microvolts, if you multiply it with the sensitivity, what you get is 10 microvolts. So, here the question asks what should be the RMS voltage. So, for a sinusoidal, it shows that it is a pure tone sine wave. So, for a sinusoidal wave, for any pure tone or sinusoidal wave, the whatever is the RMS value is obtained by dividing the amplitude or the peak value by root 2. Okay. So, this is how you obtain the RMS value for this sinusoidal wave. So, let us use this and find out. So, what you get ultimately is that the RMS voltage that is obtained would be the peak voltage by root 2, and the peak voltage is obtained by the sensitivity times the pressure peak, okay, and that divided by root 2. So, if you do this, so ultimately the answer that you get is 7.07 microvolts. This is the answer to our very first part. Okay. This is for mic A. So, for microphone A. Now, let us see what happens if the same sound wave, which is a 0.5 pascals amplitude, was now measured using a different microphone that had a sensitivity of 10 microvolts per pascal. Then what would be the RMS voltage produced? Again, using the same kind of logic and the same kind of calculations for mic B. The VRMS produced would be, because a sinusoidal, it is a pure tone wave. So, the pure tone wave generates a corresponding sinusoidal voltage signal. So, it would be the peak voltage by root 2, and the peak voltage can be obtained directly from the peak pressure by multiplying it with the sensitivity of that microphone, this microphone B, and the peak value is given to us as 0.5. So, this here sensitivity is reducing by half. So, obviously, the overall answer should reduce by half. So, it should become 5 by root 2 microvolts, which is, this is the answer for the second part for mic B, and this is for mic A. Okay. So, here now we have the answer for these first two parts. It is also asked that which microphone is better for recording quiet sounds and which microphone is better for recording the loud sounds. Now, if you think about this, if the sound is very quiet, which means that for quiet sounds, usually it means that the pressure value is quite low, or simply the PRMS in general is a low value, and we would like to obtain a readable signal. We do not want a very weak or faint signal. So, therefore, for quiet sounds, we prefer a mic with higher sensitivity, because already the RMS pressure is very low, and we would like to convert this very low acoustic pressure into a readable kind of voltage signal. So, the higher the sensitivity, the better amplified signal we will obtain. Hence, for quiet sound, mic A is preferred because it has a higher sensitivity over mic B for quiet sounds. Okay. So, mic A is preferred over mic B for the quiet sounds recording. In the same way, with the same logic, for loud sounds, if it is very loud, PRMS value could be very large, and in the last lecture I told you that the microphone themselves have a dynamic range, which means that there is a limit to the amount of sound they can record, or the highest decibels of sound they can record. And with the increase in the decibel levels, ultimately there are structural damage to the microphone itself, and they have a safe range. So, just to be on the safer side, both mic A and mic B could be used here, because both are going to produce good amount of signal, but just for the safety reason we can choose mic B over mic A for very loud sounds, so that the output voltage is within workable range, because obviously whatever is the voltage output ultimately is the sensitivity multiplied by the PRMS. Okay. this is the VRMS. So, for loud sounds, if PRMS is high, okay, so we can do away with less sensitivity also to keep the voltage within workable range, and if the PRMS seems to be very low, then we need a more sensitive microphone to obtain not weak but slightly strong and readable signals. Okay. So, here again mic B is preferred over mic A for very loud sounds, okay, and mic A would be preferred over mic B for quiet sounds. Okay. So, here the answer is mic A, mic B. Okay. So, after this, let us see another example. We have a 1.5 seconds recording of an engine noise done by a DAQ which has a sampling rate of 812 Hertz. So, various questions are asked: how many sample points are recorded using this particular setup, at what time instant we record the 500th sample, and what is the frequency range of the engine noise that can be measured accurately. So, let us go one by one. Okay. Solve the part A. So, here we are given that the total time of recording T is 1.5 seconds, okay, and the sampling rate Fs is given by, so we know that the sampling rate is inversely proportional to the sampling increment or the time interval between any two samples. So, this is delta t and this would be 8192 Hertz, and what is Hertz? We simply get 8192 samples per second. So, Hertz means that. Okay. So, we are recording 8192 samples per second, and Fs is equal to 1 by delta t. So, delta t you can obtain using this equation, it would be 1 by 8192 for this recording, which means that suppose we have got a certain sound signal, okay, and some signal is there. Then between any 2 points we have the increment which is delta t, and that recording is being done, okay, like this. So, let us say so first question is how many samples are recorded. So, here let us see here, this is our sample point 1, okay. Let me use a different color to distinguish. In this recording, this is our sample point 1, okay, sample 1, and here the recording begins with the recording of the first sample. So, the time of the first sample is 0. From the 0, that is the instant, here 0 corresponds to the instance, okay, t equals to 0 corresponds to the instance when recording begins or data acquisition begins, sound recording. Okay. So, here then we have, this is the sample point 2, this is the sample point 3 and so on. So, if you think about it, let us say I think about it, this is just the time scale and these are the times for the recording of the sample 1, this is the time for the recording of the sample 2 and so on, and finally at some nth sample, which is a total number of sample, the recording stops. So, this is given to us as 1.5 seconds, the total recording time, and these intervals here, so these intervals here are the delta t, the increment. Okay. Okay. So, you think about it, delta t, delta t, delta t and so on till the nth recording happens. So, how many delta t's are there in these n samples? You have, you start from here, you begin your recording from here, here and so on. So, there is a recording at the beginning and at the end. So, the number of points if you see about it would be the total number of the total time Here the total time is divided by in n minus 1 points. Okay. So, t divided by n minus 1. So, there is another way to write it, sorry. Okay. So, what we see is that the t total when n points are being recorded, okay, the t total when n points, where n is the total number of points that are sampled or that are recorded. Okay. Then the the total time scale is divided into n minus 1 divisions, because we begin with the first sample and we end with the nth sample here. So, here in between them there are n divisions. For example, we are making a recording with only 3 sample points. So, if you see here, this is delta t, this is another delta t. So, the total time is divided by, is composed of 2 such delta t's. If there are 4 sample points, then we have 3 delta t's within that time scale, where this entire thing is total t, and so on. So, the t total, it is divided by n minus 1 division. So, t total is simply delta t times of n minus 1. Okay. And now we have to find this n value. Okay. Okay. So, the number of sample points in 1.5 seconds should be t total by, so n minus 1 should be, so it should be t total if you solve this equation by delta t plus 1, because t total by delta t will give you n minus 1. So, this plus 1. So, if you do this 1.5 seconds divided by delta t, and delta t is this 1 divided by, you can also write it like this, you know, t total by delta t, which is equal to, another way to write this could be t total multiplied by fs plus 1. Okay. So, if you go here, n is going to be t total multiplied by fs plus 1. From this equation here, 1 by delta t is fs. So, the number of sample points if you solve this particular thing here, the answer that you are going to get is so these many points have been acquired in a duration of 1.5 seconds. So, that is our number of sample points. Let us solve, so this is for the total number of sample points. Let us solve the second part, which is what is the time at which 500 sample was recorded. So, let us see here, you know, first let us say time at which some ith sample this ith sample is recorded is denoted by the symbol Ti. Okay. So, we know that the very first sample is recorded the moment we begin the recording and acquire our first data, that is taken as the t equals to 0. It is the instance of the beginning of recording. So, the first recording happens at 0.00 seconds of the recording duration, and then the increment between 2 sample points is the delta t. So, this would be whatever is the time instance of the first recording plus a delta t. Okay. So, this would give you 1 by 8192 seconds, and T3 would be again whatever is the time at which the previous recording was done plus another increment. Okay. So, after another delta time there is a new recording. So, this should again come down to 1 by 8192 plus 1 by 8192, which is what T2 was recorded at del t time, because this is 0 plus del t. So, this gives you 2 times of del t. Similarly, T4 would be T3, the time at which third sample was recorded plus the gap between the two, which is del t, and third was recorded at 2 del t plus another del t. This gives you 3 del t. So, T1 is recorded at 0, T2 at twice of del t, T2 at del t, okay, T3 at twice of del t, T4 at 3 times of del t, which means that for any ith recording, a generic observation is that if it is a ith sample at I minus 1 del t, it gets recorded. Okay. So, you have to find out the time at which 500 sample is recorded. So, the time instance at which the 500th sample is recorded is simply T 500, which should be 500 minus 1 times of del t. So, 499 and del t is 1 by 8192, these many seconds. So, if you solve this, what you get is 0.0609. So, I am just using more significant digits because here del t is very small. Okay. So, this becomes our answer for the second part of the question. Okay. Now, if you just see by logic, suppose what is the time at which the last sample was recorded? There are 12289. So, 12289, this should be the end time of the recording where the last sample gets recorded. So, this should be 12288 multiplied by 8192 seconds. If you solve it, you will get the answer as 1.5 seconds, which gives you the total recording time. Okay, so let us see the third part. What is the frequency? So, this we have solved. So, what is the frequency range of engine noise that can be measured accurately? So, here to find out the frequency range, we have a particular sampling rate and we want to see what frequencies can be recorded. Let us use the sampling theorem. So, as per the sampling theorem, okay, which is also called as a Shannon-Nyquist theorem, whatever is the maximum frequency that we need, that we need to register accurately, it should be smaller than Fs by 2 or smaller than the Nyquist frequency, which means that the maximum frequency that we can record accurately has to be smaller than 8192 by 2. Now, in general, in practice, okay, let me solve here. So, in practice, for most of the DAQs, this has to be smaller than Fs by 2. So, this implies that Fs has to be greater than F max into 2, right. So, for most of the DAQs in practice, the Fs is usually taken as 2.56 times of the F max. Okay. So, this is the generic guideline that is used for most of the DAQs, that they want to be whatever is the frequency range of interest, the sampling rate is set so that it is greater than twice the frequency range of interest. So, usually we set it at around 2.56 times the maximum frequency of interest. So, if you think about it, you use this particular thing, then the F max using this setting should come out to be Fs, which is 8192 by 2.56. If you solve this, what you should get is 3200. So, you get 3200 hertz. So, the range of frequency range for the given DAQ setup is going to be from typically 0 hertz, and even at 0 hertz most of the DAQs that do not function 0 hertz, we usually start at 10 hertz. That is again a generic setting for most of the DAQs. So, you can take 10 hertz to 3200 hertz with a setting of 2.56 factor. Okay. So, in general what it has to happen is that it should be between 10 hertz to less than this 4096 hertz, but with the given setting usually this less than 4096 hertz is given as 3200 hertz with this particular formulation. So, this is something that is there for most of the DAQs, which gives us the frequency range. Okay, so let us solve another problem. We are given some recording setup, we are recording the sound pressure level. So, some noise whose PRMS is 5 pascals is incident on a microphone, and some kind of values are given for this microphone, some characteristics are given in the red color. Then it goes through a pre-amplification stage and some characteristic of the pre-amplifier is given, and then it goes through the DAQ and again some characteristics of the DAQ is given. So, you have to find here what is the RMS output voltage that is registered on this particular DAQ. So, let us solve the very first part. So, what we have to find it is the VRMS at DAQ. Okay. So, here what does the microphone do? The microphone converts this PRMS, whatever is input into the microphone, into some RMS voltage. Okay. So, let us indicate the input and the output from the microphone using the subscript MIC or the subscript mic. Then the V output RMS from the microphone should be simply whatever is the pressure PRMS that was input into the microphone multiplied by the sensitivity. That should give you the net output voltage that is coming out of the microphone. So, this will come out to be, the sensitivity is given as 50 microvolts per pascal. So, 1 pascal gives 50 microvolts. So, 5 pascals give 50 into 5, which is 250 microvolts. So, this is the output that is coming out here. So, here we are getting 250 microvolts as the RMS. Okay. Now, this is going through the preamplifier, and here the preamplifier some gain value is given. You know that the purpose of a preamplifier is to amplify the signals. So, the gain factor indicates that the factor through which each value in the signal is multiplied. Okay. So, here all the VRMS that are coming inside will be multiplied by the gain to get new voltage signal which is amplified in nature. So, here if gain is 1, the signal remains the same. If gain value is more than 1, the signal gets amplified. If the gain is less than 1, then the signal is dimmed down or attenuated. So, what will the PRMS? So, this V output RMS which is coming out of the microphone now becomes the input RMS for the preamplifier. So, this is what is going inside the preamplifier. So, the output RMS from the preamplifier is that it will simply take this input which is going into the preamplifier and simply multiply those values with the gain to amplify the signal. So, now the 250 millivolts that was going into the preamp is amplified by this factor, and you get a certain value which is 400 millivolts. Okay. So, this is now the output coming out from this. So, 250 volts are now amplified to 50 millivolts, which are then received by the DAC. The DAC is doing nothing further, there is no other thing given for the data acquisition system. So, no further conditioning is done to this signal and the signal is acquired at this rate. So, overall the VRMS that is being registered at the DAC will be 400 millivolts. Now, let us see the part 2, which is at what noise level will the setup stop working. Okay. So, here to stop working, and some noise level is given. So, if you think about it, various characteristics are given. This is not going to give us the range of noise level, neither this is going to give us some range, because here a range within which this microphone can work is given to us, 0 to 8 dB. So, from here we can work out the noise level range at which the system is going to stop functioning. The microphone will stop functioning once the voltage that is produced reaches 8 volts. Okay. So, here the mic stops functioning accurately when voltage produced by it exceeds 8 volts. That is the interpretation of this particular information here. So, 8 volts. Now, let us see if this is the voltage produced by the mic, the voltage signal. Okay. So, it says that the voltage cannot exceed 8 volts. So, which means that not the RMS value, but the max value, because this is, suppose RMS was set to be 8 volts, then suppose if the RMS, let us say the first case that we took that, okay, so that means that the RMS has to be 8 volts. RMS would be something like 1 by root 2 times of the voltage. This is like the VRMS. If you set this to be 8 volts, there are certain times where the instantaneous value is exceeding the 8 volts. So, the microphone would damage, it will stop functioning. So, the maximum value has to be 8 volts. So, which means you have to set the peak voltage as 8 volts. Okay. So, this should not happen. What should actually happen is this: if this is the V output from the mic, this is your voltage signal. So, this voltage signal should never exceed the 8 volts value. So, which means that this is the maximum voltages that it can reach. Okay. This magnitude should be 8 volts. The peak amplitude should not exceed 8 volts. Okay, sorry, that is not the way. Okay, given that 0 starts from here, okay, with this as a reference, the peak should not exceed 8 volts. So, then let us solve. So, when V max at the microphone at mic should be less than equal to 8 volts. This means that, so basically to obtain what is the pressure corresponding to the voltage max value, which means that the P max at the microphone multiplied by the sensitivity. Okay. V max will be obtained by multiplying the P max with the sensitivity of the microphone, and that should not exceed 8 volts. So, to obtain the range, to obtain upper limit, we will use the equality for pressure P max incident on the microphone multiplied by the sensitivity is 8 volts. This is the maximum. This is the upper limit of the P max or the P amplitude. I can say this as the amplitude of the pressure. So, the amplitude of the pressure should not exceed, multiplied by sensitivity should not exceed 8 volts. Now, let us relate this to RMS. So, the RMS of the pressure, given that it is a sinusoidal wave, for sinusoidal wave, this is our assumption, okay, for sinusoidal wave, and any generic waveform can anyways be represented as a summation of sinusoidal components. So, P RMS mic multiplied by root 2, this gives you the P peak. So, we have written P peak in terms of P RMS as P RMS into root 2 multiplied by the sensitivity, which is 50 microvolts per Pascal, okay, should be 8. So, P RMS where the microphone stops functioning is 8 by 50 into root 2, okay. Again this is, so over here you have to see that this is millivolts, okay. So, if you write everything in the SI unit, 10 to the power minus 3, 50 millivolts, this generates, because this is millivolts here, this is 8 volts here. So, in SI unit you write milli as 10 to the power minus 3 to get the pascals. So, again the value, if you solve it, comes out to be 113.14 pascals. So, this is the RMS pressure at which the microphone is going to stop functioning, beyond which. So, the upper limit for the decibels, so you can either leave your answer like this, that this is the pressure range from 0 pascals to 113.14 pascals is the acoustic pressure range for this system, or you can convert it into decibel format. So, if you convert it into the decibel format, you have the SPL for that would be 20 log 10 of P RMS, which is 113.14 divided by the reference pressure. What you will get when you convert it into decimal is 135 dB. So, you can also write this. So, usually it is written in dB, okay, the noise level where the setup stops working. So, we can say that for the part B, the setup stops working at SPL of 135 dB. This becomes our dynamic range. Okay. Now, let us see the last part of this particular equation. What is the frequency range for this setup? Again, you can use the Nyquist theorem or the sampling theorem here. This is the Fs. Okay, this is the sampling rate given for the data acquisition system, which is 16.4 kilohertz. Okay. So, F max from the previous question, we know that the setting that is usually used is F max is, sorry, the Fs is, the Fs needs to be greater than twice the F max. So, the sampling rate is usually set as 2.56 times of the F max. So, the F max is obtained as Fs by 2.56 and Fs is given as 16.4 kilohertz. So, the maximum frequency that it can accurately record would come out to be 6.41 kilohertz. So, the frequency range is going to be, let us say, typically from 10 hertz to 6.41 kilohertz for accurate recording. Usually we do not start at 0. Okay, so 10 hertz to 6.41 kilohertz. So, this solves all the questions. Now, we have a last problem in this particular topic. In a construction site, the following machineries are operative at the ground at varying distances and varying durations from a worker. Find out the noise dose percentage of the worker. So, a table is given that these are the different machineries operating on a factory floor, and it is in an open field. Considering that it is a construction site, it is an open field environment and the machineries are kept on the ground at the varying distances from the worker, and this is the sound power level of the various machineries. So, let us see, let us deduce what should be the SPL that is heard at the worker location. Okay. So, for that, if we take just the schematic of one simple machinery, suppose this is some machinery A, any kind of machinery, and there is some worker here. So, this machinery here emits the sound waves in the free field. Given that it is kept on the ground, it will get a hemispherical wave front, okay? Not spherical, but rather hemispherical wave front like this. Okay. So, whatever this is the sound power level that it is emanating, and at the worker location some sound intensity level is heard. Let us relate the two. So, what you have, the intensity, the RMS intensity should be the whatever is the power divided by the area or the wavefront area, because it is kept on the ground. Here we have a hemispherical, the hemispherical area. So, we take the area of the hemisphere. So, this should be actually 2 pi d square. If suppose it was suspended somewhere in the air and acted as a point source, it would complete a full sphere and it would be 4 pi d square. So, over here we take 2 pi d square, okay, the power divided by the area, and then you do this calculation, and then you do the 10 log 10 of both the sides. Okay. So, what you get is this WRMS by 10 to the power minus 12 minus 20 log. So, it is 10 log 10 of d square, which becomes 20 log 10 of d, this particular value here, and this 2 pi is separately minus 10 log 10 of 2 pi. So, if you see here, this is what we are getting. This becomes our SPL at the worker location. Okay. This is the SPL at the worker location, and this is the sound power level of that machinery okay, and this is the distance between machinery and worker. Okay. So, once you solve it, this 10 log 10, this thing here, this becomes your LP, this becomes your LW or the sound power level minus 20 log D and 10 log 10 of pi, sorry 10 log 10, so 20 log D divided by 10 log 10 of 2 pi, okay, here 2 pi. This if you solve it, it comes out to be 8. So, this is the equation that is deduced for this particular problem. So, using this equation now we can obtain what is the SPL received at the worker location. So, with the same we use this particular formulation, we put LW which is the SWL, okay, and we find out the SPL at the worker location. It comes out to be these values for the different machineries, where this is the distance D. Okay. So, now we have the SPL at the worker location. We can use the noise dose formula which is given by this, where every Ti for the NIOSH guidelines is given by 8 by 2 to the power Li minus 85 by 3. So, all of this we have covered in our previous lectures. So, now let us see, this is the actual duration of exposure, this is the level at which these exposures are being done, and by the NIOSH guidelines this should be the maximum permissible durations for these particular levels. So, the noise dose can be calculated by doing 4 by 16 plus 1. So, the actual duration, so it should be a summation of the actual duration by the maximum allowed duration. So, you see this, you compare this row with this row and you see 4 by 16 plus 1.5 by 8 plus 1.5 by 7.29 plus 1 by 0.63 multiplied by 100. So, overall you get a 223% of noise dose, which means over exposure to hazardous noise levels. Okay. So, this is how you can solve the various problems, and with this I would like to close the lecture. Thank you.